So as far as GAN is concerned, not just GAN, even other deep learning methods, even for generative modeling, architecture also plays a major role. That's why we are also looking into architecture, because sometimes you have maths ideas, but then there is also engineering, which is also important, equally important. So engineering usually means that you go into the architecture, play around a little bit, do some normalizations, do scaling, downsampling, progressive scaling. So there are so many ideas there that requires understanding of the architecture used there. So that's why we are doing CNN, and based on this we will discuss maybe 5-6 more prominent GAN-based architecture. So we were doing CNN basics, and these slides are taken from deep learning course in CMU. And all this we have seen in the last class, so for the first part I will go rather quickly. So there are cases where we are looking for some portion in a sample, okay? There are samples like that. So in this case it could be audio data represented in some form, look, and let us say it's 1D. Then the word welcome will have a certain corresponding heat map. So that's there is some activity like this, or let's say the amplitude, or which will correspond to the word vector. So when there is a data like this, where I'm looking for something small in the big sample, then using whole MLP is really not very useful, because whole MLP, if I want to build to detect a word welcome can appear anywhere. Then it is as if like I need many samples with this word welcome distributed in many different ways. Okay, but ideally what I really want is just something that can identify the word welcome in a small region. So essentially what we saw in the last class is what really we are looking for is a scanner. Okay, we are looking for something in a bigger chunk of the sample. So that's why we diverge from the usual artificial neural network and go into a new architecture where we scan. Okay, so this is how we can scan. So scanning obviously means that there will be some window over which we are going to scan. And these are the things which is very not just in the audio data, but these are the things which is also required in the image data, where you are looking for something specific in the image. Okay, so in this case, let us say these are flowers. So here there are like 4 places where there are flowers. So this location of the flowers is really can be anywhere, right? So it's kind of, you're looking for something which is robust to shift. Okay, or in other words, it's a shift invariant. So again, the usual idea that I will scan should work in these cases. Okay, so so how we will build a multi-layer perceptron that can scan a flower, which could be anywhere. Okay. So like this, so we should, our MLP, the multi-layer perceptron, should be able to identify that this has a flower as well as this has flower. Okay. So, and same thing also goes in the audio case, which we see this as one-dimensional case. And so we can start with one-dimensional case, and then as if we are scanning this via some MLP. And obviously, this is the same MLP which is scanning different regions. So it will go from the start to the end. And each time it will have certain weights. Obviously, it will train those weights during training. So after training, it will learn to identify, okay, so whether welcome was here in this region. So the data here in this window will be processed, and then they will give some probability output of for occurrence of the word welcome. And if it so happens that it gives you output, let's say very close to, let's say it's kind of like a probability value, so let's say 90 or something, then you can more or less say that I can identify that as welcome. So same happens with the images also, right? Okay, so these are the things we have seen already. This is a 1D segment. So here you can see the segment that we are extracting is just one-dimensional. So current location T, and I go to K more pixels from my current location from T. So this will extract a chunk of size K. This is one-dimensional, right? Once I have extracted that segment that I'm going to scan, obviously it goes through MLP, and let's say in this case it's compute some some output, okay, or it creates some probability values out of that using softmax. So that's how we are going to decide, okay, whether the word was there or not. So another view is that I see this MLP as a scanner, but I could have seen multiple copies of this, one after the other. And then I could have said that this is one big giant MLP, but it's just that there are multiple copies laid down over the one input sample. So there is another view of that, but the only difference is that now you will have weight sharing. Okay, so this is another view, and that helps during training. So we won't go to the training portion of the CNN because training usually is taken care of by PyTorch and so on, and usually it is not required in the engineering aspects. Sometimes, although it is also required, but many times we don't need that. Okay, well, similarly, we can do scanning in 2D. Now it's just that I have to go right and also down. Now, how many steps you go right, how many pixels you go down, it's a hyperparameter. We call it stride. So, but anyhow, the whole idea, the generic idea is that I'm going to scan over certain window filter size or window size in this case. Okay. So the idea extends basically in the 2D case as well. Go certain stride, okay, right, and then go down also, okay, and eventually kind of complete the whole scanning. And again, like before, this is the same MLP that is just scanning through different region. And it's not a problem even if it's same MLP, because once it sees this region, it calculates the complete probability for that, and this guy is saved. So it's not like I lost the data when I went to some other area, because this output is now saved as Y something we saw. So that probability of whether flower was there is saved there. Now it goes to another region, that probability is saved there. Now obviously it has its weights that are learned during training. So these weights correspond to flower detector. Okay, so this will be trained during supervised learning, build a loss function and so on. So these weights will be such that when it takes this input, then it produces the probability that it's flower or not. Okay, so we are assuming that for the moment that this it has learned. Okay, so the weights of the neural network are known. Okay, and then we are thinking how it will scan and then how we will infer, right? So we are mostly into inference right now. So these are the phases of how you will use small MLP as a scanner. Okay, which is really required in images. Even if you have gone for a full MLP and don't want to use a scanner, then just because these are images, things become kind of like explored, because there is so many possibilities that flower could be there. Okay, so using full MLP to scan this for various samples, because sample itself could be, there are so many possibilities. Okay, color images has RGB, and each pixel can vary in many ways. In the SIFT, they can vary in many ways. So this was a natural way to do this. Okay, and there is an argument that even our eyes work in a similar way. Okay, so maybe the neurologist will say those things better, like how they understand those things. But kind of inspiration is somehow, if I understand correctly, taken from there. So there are like earlier papers that I can cite later. So idea here is, yeah, so it's more or less, this is what we are going to do, produce the output probabilities and then take the max and see that it's really, you can conclude that there was a flower or not. And again, changing the 1D scanning to the 2D case is rather straightforward. It's just that I need another index j also. So I have to go to the how many pixels to the right, and j maybe to go how many pixels to down. Okay. So, and we are assuming that this scanning windows are of similar k by k size in each direction. So we can say that it's k as well as k here. K pixels to the right, k pixels to the down. Okay. So this defines our window size, and you can adjust these loops so that you don't fall over the scanning image. Okay, so you should go only up to w minus k plus 1, otherwise you will fall over. Okay, unless you do some additional padding or something, which is also possible. So this should be adjusted in that way. So these ij are nothing but basically the pixel number in this case. Okay, so so basically the segment is taken, in this case it's k by k segment of the image, and then we apply the usual MLP, and these values are saved. In this case the output can also be ij, because these windows after scanning give you ij value, right? So then these outputs are also like a matrix. And obviously as a last step, you can do the softmax to find out whether there was flower or not. Okay, so as usual, the usual notations are k by k was the size of the patch being scanned by MLP, and w is the width of the image, and h is the height. Okay, so j is kind of going downwards, I going horizontally. So this is a simple scanner in 2D case. We can scan that. So again, if you would have used a full MLP like so, then the whole MLP, let us say these are the vector representations of the whole sample, then essentially you need this big MLP to scan this current sample, and in that case you will have so many weights. So let us say there are n, then there will be like so many weights here, and there are m neurons and inputs into n by m matrix. Okay, because each is connected to all, right? So one is connected to m neurons, second input is connected to m neurons, so that you will get n by m input. Okay, so in a full MLP case, as you can see, there are a lot of weights there. Okay, there is no sparsity obviously, but this is not what we are going to do. So we are using a scanner. So in that case, the picture will be like this. So this is how we are doing things, right? It's just scanning things. So in this case, the weights will be kind of sparse, because this is the same MLP being used here, same MLP being used here. So compared to the full MLP, now it's like these guys have nothing to do with this. Okay, so basically it will be a block diagonal matrix with the blocks each identical, right? So this is the picture. If you want to see this as a full set of weights for the given sample, then this is the weights of the first this guy, and this is the weight for this guy. Let us say only for this layer. Okay, so let us say only for this layer for the moment. Similar structure will appear if you go from here to here. Okay, because this is again kind of shared. So so as if if you look here, as if it's like these weights are just copied here. Okay, because it's the same MLP. Okay, so we will look into this shared weight and how you update those weights. Okay, so so in again in 2D case it's the same picture, so I don't have to kind of, so you do the scanning and then you with the same MLP, and then you produce the output. So just some remark on the, as I said, I will not go into the training part of the CNN. This is more or less taken care of usually. This is also taken care of forward process, but some engineering happens here during GAN training. That's why we are doing this. But training for CNN is a little bit tedious, okay, because there is a lot of stuff there. Max pooling, small filters, weight sharing. So one has to be a bit careful when updating the weights. So you can watch the CMU lecture if you like, if you want to understand the training part as well. We will not do that. Okay, so but I will just give you an intuition what happens. So this is a shared parameter network. That's why we call it shared parameter network. For a given sample, there is a network which is operating in chunks, and as if it's giving me a feeling that it's kind of, it was like a one big network with shared parameters. Okay, so that's what we mean by shared parameter network. Okay, so network is visualized as multiple copies of the same. Okay, so so in this case, this blue circle, oval circles are kind of, ovals are shared, indicates that these are the same network. So if you just look into the update part, okay, in a very simple way, as I said, the whole update process is a little bit interesting, but just to give you a small intuition of what would happen if because I'm supposed to update the weights of the network, right? So how will the weights of the network get updated when I have a shared parameter network, right? So in this case, let us say this yellow region is a shared edge. Okay, obviously there will be other edge also, but we can focus on one specific edge that is shared. So in this case, we call it is shared. So you can say that this was the region. Let us say this is the network, and this MLP just moved a little bit next time, right? So let us say this is the network next time, right? So this is a scanner, right? So first time it's here, second time it's here, but then this edge was the same edge, now it moved here, right? So that's what we mean by shading. So then the idea is like, during training, what will you do, right? Because these weights were here, and you computed some loss, and then these weights, same weights, now you're scanning other region, and it will affect the loss again, right? So how will you update the weights? Because these weights were previously scanning another region, gave me different loss. This is scanning another region, it's also giving me another loss, right? So so we can formally, using some maths notations, we can say that, let us say Wij is this guy, and let us say WMNL is this guy. In a very generic sense, we are saying, okay, wherever they are said, it doesn't matter. So we can say that this is like Wij and WMN. Okay, let us say, okay, we can make it very formal. Take a set S, put all the shared weights in S. Okay, so one can do that. But so let us say this guy Wij and WMN are shared weights. So let us give a common name of these weights at WS. Okay, meaning shared weights. So ideally, what I want is that Wij is required to be identical to WMN, obviously. So Wij is required to be equal to WMN. Okay, so how will this influence the loss, right? So this is the question, right? So for any training instance X, a small perturbation in the WS, the shared weight, obviously perturbs both identically, obviously. So each of these perturbation will influence the divergence. So in this case, it's a good idea to look at the influence diagram. So this is the loss that is being created. So while the first MLP was scanning a certain region, so these were the weights, the notation that we gave, although they are the same, but let us say this was Wij, and then this was WMN. Okay, so but then I am supposed to compute the derivative of the loss with respect to that shared weight Ws. Okay, so how we will do that? So we can use the calculus that, okay, if the function depends on two variable and arrow goes like this, then obviously, like by chain rule, I have to go derivative of this with this. Okay, and then derivative of this with this, and then derivative of this with this, and then this with this, and then sum, because they are combining here. So from the chain rule, we know that we do derivative of this with the Wij, this branch, and then in this branch I have Ws here, so I do that, and then derivative of this with this branch, and then with this guy with this Ws here. But we know that Wij and Ws were the same guy. So that becomes 1, obviously. So this guy actually is 1, and this guy actually is 1. So eventually everything boils down to just this sum of these. So if we are doing training, and if while scanning and you got some output somewhere, the loss was like that, then you use this guy, and then when your output was affected then by going to some other location, then so basically the shared weight updates now goes with this derivative loss with W and derivative loss with Wij, and then with WMN. Okay, so yeah, so this is something you can just keep in mind, but as I said, we are not going into training as much. So as such, you can really make things very formal. So you can say that there is a set S with, let us collect all the shared weights as E1, E2, En, and call it S. So in general, what will you do by just extending what you have done before? Let us say these guys are all shared, and these are denoted by the red arrows. So these guys are the shared. So let us say it's E1, E2, En. Then if I have to update the weights of my network Ws, then I should essentially just sum over these derivative, okay, with respect to these weights. So that's it. So that's more or less, you will do the same thing for these guys. Okay, again, these guys are shared, and then you will update the weights in the same way. So and then the usual gradient descent, you need to kind of update your gradient descent with this. You sum over all the shared weights. Okay, so gradient descent, this is the usual gradient descent, but then it's just that now we are taking derivative with respect to the shared weights, and we take care that it gets shared weights changes get added in the loss, gradients get added. Anyway, so training, as I said, the full scale training is pretty complex, so we are not going to do that, but just to keep in mind how. Okay, so we will further continue a little bit with the scanning. So this is as usual, just repeating the same thing. Okay, so we scan like this, and then at each location, each neuron computes the value based on your inputs, and That's how things work. So this layer takes all this data, and then on this same input, the output is produced right there. Okay, right there, all the things are there. So, and this continues for each window, obviously, and this is how the softmax is applied at the final final output. Okay, so this is one way. So the reason why I'm saying is like one way is that you can just change the for loops a little bit, and you may get a different variant. Okay, so what you are saying here is that let me fix the window, and then let me go the for loop for all the neurons in the current layer. But as I said, now algorithmically you can do it in many ways, right? So what if I fix the neuron, and then go through all the what if I fix the neuron and the layer, and then that fixed neuron now scans through everything, and then the computation goes to the next neuron. Okay, so if you think of this as an algorithm terms, just by changing the for loops, okay, because in this, if you think in terms of algorithm, then the way things are right now, your top loop is for loop will be for the scanning region, right? So let us say this is like time for loop, right? So this increment is the slowest, right? So that goes at the top. So for time, for this current window and so on, that's your first for loop. And then you are saying for the current layer, so this is our first layer. Okay, so for layer 1, 2, 3 in this case, and then for that layer, the innermost loop will be for the neurons for the current layer. So in this case, it's 4, right? So as I said, now you see the algorithm, right? So now the whole idea is like what happens if you flip some of these for loops, and it looks like a different style of scanning. Okay, so basically this is what this next set of slides are about. So let us do the computation in a different order. Okay, so if you do computation in a different order, then this is what is happening, right? So let us say the first neuron, I hope you can see, this is the first neuron, or this side actually is the first neuron. Okay, so this first neuron is now, only the first neuron is now scanning. Okay, so only the first neuron is scanning, and it has scanned everything until here. Okay, and then I believe the second neuron will start scanning. Okay, so this is now the second neuron will start scanning, and then the third neuron will start scanning. So second neuron in here, you can see clearly second neuron is done. Okay, after the first neuron, second neuron had also completely scanned. The third neuron is now going to start here. Okay, so in this case, let us say the second neuron is done. Okay, then the third neuron will be done, and then the fourth neuron will be done. Okay, and then the next layer neurons can start. So now this neuron using this, because this neuron needs data from the previous four neurons, right? So this can calculate this, this can calculate this, and this can calculate this for all 4. Okay, so this can produce this output, and then let us say this neuron is now done. Okay, this yellow neuron is now done with this its own output. Then obviously recursively this neuron will now produce its output. Okay, so basically what we have done is like kind of the time window is the innermost for loop. Okay, that's why this is running the fastest, right? So this is what is happening by the second neuron, and it's done computing its value, and then finally this third layer neuron has started computing because it has the data that is needed now. So it will start scanning this, and then finally it is also done with this computation here. And so let us look into this for loop. In the for loop, so in the for loop we have the time component here. So time is basically the scanning part. So scanning part is now at the top. So this means that the window is kind of fixed, and I want to do everything on the window. Okay, so this is the old idea, right? Fix the current window. So that's it, the slowest loop. And for that fixed window, fix the current layer. Let us say the first layer. In that first layer, for all the neurons in the first layer, D sub L, this is sub L. So let us say D1. D1 will be the number of neurons in the first layer. So all the neurons in the first layer, because this is the innermost loop, all the neurons in the first layer obviously will kind of now process that. Okay, so this is the innermost part. This is what is happening here. The innermost one is the first neuron again is kind of So the segment you computed here in this loop, right? So here from your current time to the, because the segment length is k, so because it's one dimensional case, right? So we got the region that we want to scan, so that's there. And then we have I loop I equal 1 to dl minus 1. So for generality we have put dl minus 1 because your current layer neurons will be accessing the number of outputs from the previous layer neuron. So we have written this in a layer oblivious way. Okay, you can think of. So if I have to draw some picture here, then let us say this is my my L layer neuron. So this is my DL. So this is my okay. The way we are writing is bottom to top, right? So let us write like this. So this is my DL minus 1, and this is DL, right? Okay. At the first step, obviously, at the first step you have image segment, but image segments I can see this also as dots. Let us say, like if you prefer like this. So this is my kind of like D1, okay, D1. So then, so ideally, so at layer L, what is happening we are saying, right? So whatever output that was produced by L DL minus 1, meaning the number of neurons in L minus 1 layer. So these are the number of neurons L minus 1 layer, and these will be now used. These will be now used to compute the data for the first neuron, which is the jth loop. Okay, so this is this, and then this is I equal 1 to dl minus 1. So this is our dl minus 1. I equal 1 to dl minus 1. So use this, and then to compute this. Okay, only for the first layer we have separately defined y to be like this, which is actually a window segment. But after first segment onwards, these are just kind of, so here only for the first one we have separately kind of said what is our y, which are indeed the segments. But from second layer onwards we are just kind of using that all these. So all this will be used like this, right? So another way to say is that this MLP kind of scans these windows. So this is our, let us say, 1D data. Then only kind of in the first layer, okay, so this neuron is kind of all the neurons here are kind of, all the neurons are scanning all these inputs initially. Okay, and then so because they are all working on the same window right now, and then from here onwards it is like this. It's like full MLP. Okay, so from first layer is neurons are only focusing on the chunk because it's like that, it's a scanner. But second layer onwards, and they just access everything from previously. Like second layer onward are not doing the scanning like you may think. Okay, so it is not like multiple level scanning. That's what I'm trying to say, right? So second layer onwards we are not doing scanning like this. Okay, we are not creating further window. So this window thing is happening only in the first input case, which has been done as a special case. Y0 is handled for layer 1, and otherwise it will kind of look into all the previous. So if we look into this now, this part now, so let me change. Okay, so what is happening here? So for I equals 1 to dl minus 1, so here I equal 1 to dl minus 1, so W weight is there, and this is L. Okay, so this L, first one is L for the layer. Okay, so let us start with the first layer. Okay, so let us say the first layer, L is 1, and then I, in this case it depends, right, vector entries or whatever you are going to kind of scan from here. Okay, so in the first chunk, right, so this is your Y now, and then yeah, and then we have the J, which is the current neuron. Okay, so this is your current neuron of the first layer, and current neuron is doing inner product with dl minus 1. So if you are thinking of the first layer, then dl minus 1 will be some of these points. Let us say in 1D case, right? So this is what is happening. Okay, dl minus 1 is reduced to these. Okay, so L is 1, right? Okay, so let us say dl minus 1. If L is 1, dl minus 1 is 0. Okay, so we can say that this is the 0th layer. So in 0th case, you are just accessing these guys. Your I loop is just this. Okay, and this is for the first neuron, and then obviously J stands for the neuron. So then J will change, right? So then J will be 2. Okay, so that then J will be 2, and then this I for the second neuron, again they are going to access these entries. Okay, so this is happening in the first layer, let's say, or 0th layer, let's say. Okay, first layer, yeah, I mean we should call it first layer because the loop is L. So I hope this is clear. So if you look into the weights, then these weights are like that. So each neuron can take a segment, and these weights are vector, right? So the way we understand, right? So each neuron is responsible for doing W transpose X plus some bias. Okay, so each neuron is capable of taking big chunk. That's what we know, right? X1, X2, Xn. Okay, and these are the weights W1, W2, W3, and so on. So this weight that you see is for each neuron. Okay, so L is 1. So if I have to write down, then this is W1, and I is varying. Okay, so this I, if I have to write this in vector form, and then this will be, let us say, I D0. Okay, this is the indexing for the I if I have to vectorize, right? But now things are happening in a pointwise way. Okay, so this is why, that's why you say I, and J is that neuron. Okay, so the Jth neuron, right? So all this is happening in the first layer. Okay, so we will vectorize this later. So what is happening here, if you see, then this is just W transpose X. Okay, you can incorporate the bias by appending 1 somewhere here. Okay, usually that's not an issue. So that's what is happening here. 1 W transpose X is being done here. 1 neuron is active right now in this operation. Okay, obviously when Y will change to 2, then another neuron will come with its own weight. L is still the one, J will become 2. So now the second neuron is operating. Second neuron will be operating on that window. Okay, so that's how it is. So this is the linear combination part, and we also know from the ANN. Then we also go for the activation later on. Okay, immediately after linear combination, usually we do activation. So in this case, we did that activation, and then we store that value here, right? So that's the flow. Okay, so let us revise this again. So we fix the window, which in this current variant, we fix the window, and then we do the full processing. Okay, so we fix the window. Let us say we are right at the first step where our input is actually the segment. Okay, so this segment in the very first step, this segment we will call it length of this segment. We will call it L. So if L is 1, then the first segment length will be L minus 1, which is D0. Okay, so at the very first step, we are working with D0 length. So these are the points, number of points in that, because it's a 1D case right now. So number of points D0, and that many weights are required, obviously. So that many D0 weights are there. So then I do W transpose X plus B. So that's that effect going on here. And this happens here, and then I get the JAD output, and then I do the activation and so on. But obviously I don't exit, obviously, because this J it has to be done by all the neurons. So right now I have only faced the first neuron, and then I will go with the second neuron. I will go with the third neuron, and so on. So DL means number of neurons, right? So in this case, number of neurons, in our case here, 1, 2, 3, 4, 5. Okay, so then the second neuron will do the scanning. Okay, then the third neuron, J will increment, third neuron will do this and all, and then this data will be produced. Okay, because after doing W transpose X plus B, you just get one value. After doing activation also, you just get one value, right? So these are just one value for one window, one neuron is giving me one value, okay, one output, okay. So this y is saved, right? So this is being used again and again because in the second layer, so let us say your while loop is done. So this you are done with that. Now you will be here, okay. So here you will, okay, let me, so we are done with this guy, let us say the initial one which was working on segments. So that is clear for us. Now these guys at the second layer is now going to use the previous layer, right? So so in this case this dl minus 1, right? So this was our d0, this was our d1, okay. So now if I'm at l equals to 2 or yeah, l equals to 2, then this is my layer 2. Then I am looking at dl minus 1. So dl minus 1 was how many neurons you had in the previous layer, which is d1, okay. And now it is kind of not using window, okay, that's the point. Now it is accessing all because dl minus 1 was number of neurons in the previous layer, okay. In the very zeroth step, okay, we were restricted in a window, but from second layer onwards they are just doing weights computation. They are using all the previous outputs, okay. The no concept of window anymore, okay. Use everything from the previous outputs and you keep doing this recursively, okay. So that's what it's being done here overall. And now it's a question of playing around a little bit. You just change some of these for loops and you will get a different variant, okay, which sometimes could be interesting. There is something called hierarchical scan, and in those cases sometimes changing the loop will be maybe interesting in some cases to create some new variant, okay. So we will see how now what is being suggested is, what if you change the L loop and I guess the T loop. So basically or we already changed, I guess. So T was here at the top, now we changed, okay. So we move the T down, and L and T ordering, L and J ordering is kind of same. So J follows L. The only thing we did is that we moved the T loop right below. So that's what we did, okay. L, J ordering is similar and the T is at the bottom, okay. So you can verify that this won't change the computation, okay. Sometimes just to change the loop you have to be a bit careful that did you not kind of change the computation, okay. It can happen if you change the ordering, sometimes computations may not be the same. So one has to be careful that it's possible, okay. So if it's the case, then what you can assume now is, since the T loop is the innermost loop, it is the fastest loop now, obviously. So this means that you will scan over all the time windows, okay. So all the things that you have to scan, that you will do first, okay. And then you will go for the neurons, and then you go for the layers. So okay, so if we see this flow, then it's saying for the current layer, so let us imagine any layer, and then for that layer all the neurons in that layer, okay. And then we fix some neuron in that layer, and that neuron, that fixed neuron now is supposed to go through all the scans first, okay. So this is something we discussed previously, right, when we said let us do in different order. So let that one neuron scan through. So this is what is happening just by changing a loop. Now we are doing that, right. So more or less other things remain the same. So still does not change the computation, and this is something I may leave this as an exercise, that doing this doesn't change the outcome, okay. Okay, now we can vectorize also. So what we have vectorized, we had L and T, and now it's also one more change, L, T, J. Okay, this is one more change. So I also I made the J loop at the bottom now, L, T, J. Yeah, this is different from all, okay. So TLJ, LJT, LTJ, okay. So there are like 3 variants we have seen, okay, and all doesn't change the computation, okay. That's interesting. So I guess one of these is useful if I want to vectorize, okay. So I guess LTJ loop, okay. That's why we came here. So LTJ loop is easier to vectorize, okay. So vectorization means that can I change pointwise operations to vector operations, or even matrix vector operations, and usually doing that is useful in computing, because you can use some existing very good libraries like BLAS and LAPACK and so on. These are linear algebra libraries that work very well in blocks. Okay, so it seems that we could vectorize like this. So if we have to look into this vectorized part, so what is happening is layer L. So this is the layer. So layer wise, okay, it's at the top, and then for the current layer, go through all the windows. So for a given window, it seems like all the neurons want to do it in a vector form. Okay, so this is what this is saying, right? For the current layer, current window, all neurons have kind of trying to exploit the vectorize. So this segment remains the same because this is the current window. So segment is extracted, and then what is going on here is like as if all the neurons have stacked their weights because they are supposed to act on the same chunk y. So they have kind of stacked the weights, and they all can do the weight W transpose input x simultaneously, right? So one neuron previously was doing W transpose x, another neuron, and since all the neurons are acting on the same window, this guy is also doing but this neuron has different weights obviously. So let us say this was W1, this is W2, but acting on the same x. So one possibility would have been that why not stack this, right? So W1 stacked with W2 like that, okay, and maybe let's say transpose and then stack, and then they are working on the same x, and then this produces the Z, which is also indicated as a vector, like a bold Z. It's like a vector. So this is what we call by vectorization here. Okay, each neuron all were applying their weights on the same segment, so we could have stacked them by doing that J loop inner, and then this is vectorized. So if you call some linear algebra libraries BLAS or something, then this is matrix vector. So it will be I think one level BLAS. I think it's called there are like 3 BLAS levels. Okay, so I think one level is like matrix vector, third level is like matrix matrix. So the higher you go, better it is for exploiting the cache. Okay, less cache miss will be there. Okay, so we could vectorize the loop, and the idea would be very similar. So in the 2D case, I may go a little bit faster. So the similar thing can be done in the 2D case. It's just that now you have to maintain two for loops for height and width. So basically only for the chunk part, right? So this is how it's happening in the current neuron. Has all the weights for each of the pixels in this window. Okay, so there are as many weights for the current. Current weights are involved with the neuron, so that it can do W transpose pixels, all the pixels in this window, and then each time it adds one bias term as usual, and then it produces one output. Obviously, okay, that's how each neuron does, right? Okay, so more or less the idea will extend in the 2D case. So each neuron is scanning like this, and each red window that it scans, it gives just one output. Okay, but the fact that it's going right with some stride and it's also going down with some strides, it will also end up with producing some output like this, because each scan is giving you one blue dot, and then if you keep doing that, depending on the stride, how many of these output will be there, it depends on the stride. If you are doing only one stride, then more or less will be very close, may not be exactly, but may be close. So one neuron is, after scanning a 2D image, one neuron also produces a 2D output. Okay, so this is what is happening with the first neuron. Now you can do this with the second neuron as well. So second neuron, and then the second neuron, let's say, did that. Okay, and then it produced its own 2D output. Third neuron also produces its own 2D output. Fourth image also produces its own 2D output, and then from here onwards, there is no concept of a window. So here onwards, you just take all of these guys and just like kind of like take a linear combination and activation. So from here onwards, you can just treat them as just looking into all previous ones and then doing the weight updates, applying the weights, and so on. Okay, so we may look at this like that, and then finally we have an output which, in this case, if it's a classification problem, then it will produce one output eventually saying that it's an MLP. Okay, so so again, as I said, for each of these thing that you see here, outputs that you see here, each neuron will use all the previous outputs of the previous neuron and combine them to produce one output. So in this case, it will use these 4 outputs to produce one output, and then another one to produce another output. So this way, both the neurons have started working on the previous layer neuron outputs. So this way, now what you see is all this has been used by these neurons, and they produce these outputs. Okay, let us say if you focus on these, then these were produced by the processing of neurons on these specific inputs. Okay, that led to this specific output, and then finally we can combine them again by one neuron, and then with all this combined, it will produce its one more squared output, obviously. So and then you may kind of make it into vector and then classify based on that. So that's what we did. So finally we made the last neuron output was also squared, but we can make it into a vector, and then we pass it into a usual MLP. Okay, so usual MLP here is like fully connected network. Take all the inputs and then start producing. But until then, what was happening was these guys were being used to produce one output. Okay, the corresponding entries here were used to produce this output, and then corresponding another entry here were used to produce some other output, and so on. Okay, let us focus on this red window, right? So let us focus on this red window here. Then this. So the way things are happening here is that we fix on a window, and all the processing happens on that window. Okay, and final output is produced. Like this is one view that we are seeing, right? So in this view, where I fix a window and I go through and produce a final output, right? So this is why you see here for this fixed window, this output got produced, this output got produced, this output got produced, this got produced. Immediately this got used, this got used. I'm still on that window. Okay, I'm not moving around. So it got processed, and then finally, so I could have just focused on these guys. That's what I'm saying. I may not have needed anything else, because this output that I have produced is just specific to current window. Okay, so this is the view we have, right? We fix a window, we produce the output corresponding to that window. Next layer neurons also go ahead and use outputs produced by the previous neuron on that window, and then produce a final output. Okay, so this is what is happening. So this is where it's like the time loop is at the top. Okay, so time loop, the window is moving the last, right? So fix a window and then everything happens. So this is why we just have to look into these 4 dots. Ideally, if no other dots, all other dots vanished also, I don't care, because so I just need to focus on 4 dots, final output, save it, because I need it as softmax later on, but that's it. Okay, so I hope that's clear. It's not really needed that I save all this, right? That's what I'm saying. So okay, so that's it. So that's the full flow, how it works, and then finally we have MLP. And in the 2D case, as I said, I can go over on this. It's not really much here. In the usual case, we take it's just the scanning part. So you take a chunk. In this case, it's k by k chunk. So you have taken the k by k set of pixels in this case, and that is your segment. Your MLP applies on that and creates a softmax. Now we can write that in a little bit more detail, like we did in the 1D scan. Again, there is not much, to be frankly speaking, not much changes as such. So this is the case where the time loop is again the slowest. So this is our time loop. Obviously the time loop was for the window, so this is our time loop. So that's where at the top we have, let us choose what is to scan, right? That's the window. So let us say we choose some k by k segment. So this k by k segment is taken here. So this is the k by k segment. But what you see here is 1 to C, right? That's a little bit interesting part. It's called channel. So we can see that in the second part later on, because so far what he has said is like there is one 2D image, right? But then what this says is that there could be color image, and color image comes with three 2D images, right? RGB, right? Anyway, so if that is the case, then even the segment that you are taking out will be a kind of a cube with three small cubes, k by k patch. Okay, so if it was done on color images, then this patch will be like this, out of this bigger images. Okay, so this is our channels RGB, and then the window that we may be looking for is this one. Okay, so this will be my channel 1, this is my channel 2, this is channel 1, channel 2, channel 3. Okay, so this so the segment that you are going to take out could be like this. Okay, so we will come to that. Okay, that is like just a cosmetic thing, how to do it for this, but the main ideas we already kind of go through. Okay, so what is happening here is that this part, I'm not sure if that is being used here. So you can think of these as just one here, okay, just one channel. So you are just scanning one image. That's a grayscale image. Okay, so it seems like for our purpose it has been kept to be 0. Okay, so that's our image segment. So we have extracted a k by k patch, the current patch, and this is the usual way, right? So we first pick the patch and then we process everything on that patch. So then you go from 1 to number of layers, and then for a given layer, then you go to number of neurons. So this is d sub l, not 1. Okay, so L is sometimes looks like 1. Okay, so in this dl, so go for number of neurons in the current layer. Okay, and then this is pointwise. Okay, we have not vectorized this yet, so that's why you see that for the current neuron also I have to kind of extract all the pixels so that I can do the W transpose X. In our case, X is the segment, right? So this is the segment, so we are doing pointwise operations. So this I is denoting the number of pixels. You make it into vector so that you can do inner product. Okay, so can you see that? So what happened here is that y as such, y was your image segment, right? So as such, the y input was like this, right? Where you have you have your x and y like this. Okay, but then this segment has pixels, right? So these pixels are now, we use I to kind of count this and make this into one big vector. Okay, so this I will be these guys. And similarly, we kind of do that for this guy, right? So these are the weights, and then the corresponding pixels where these weights are going to apply. So this is our y, okay, this guy, and the weights. Okay, so then you do pointwise multiplication of these guys. Okay, and then you store them. So if you are doing PyTorch, you may have to do reshape and things like that. Okay, to sometimes make it to vector, sometimes go back to square segment and so on. Okay, but these things are simple. And then so basically you do that. Because we do pointwise multiplication, right? So some weight here multiply some weight here. So that's one value here, right? So you keep doing that, but then you add, right? So because it's an inner product, right? So it's like W1 X1 plus W2 X2. So that's why you see this plus here. Okay. So you do this pointwise W1 X1, W2 X2, and then you keep adding. Okay. So after doing that, you just get a scalar. Okay. So this is just a scalar, because after inner product you get a scalar, right? And then you just have to apply some scalar activation function. It could be sigmoid, ReLU that we have seen previously, and that gives you one output. Okay. So this is the 2D scanning part. Okay. So do you have any doubt or any question until now? It should be okay, I guess. So here what we are doing is that we are doing 2D scanning, and in 2D scanning we for the moment, let's say we are doing 2D scanning and we take a segment. So this guy is a segment. And then we do some algorithmic things to identify what is this segment, which is given by X and Y. And then once this segment is found out, this I loop is used to kind of track these pixels in the segment. And then the corresponding weights are applied. So right now the current neuron is working, let us say some Y as some J. Okay, so J stands for the neuron. Okay, so some jth neuron is working on this current patch, and I is just used to kind of make this into a vector, and the neuron applies its current weight. So in this case, let us say is the first layer, then 1, and I is obviously the weights that is has, and then J is the current neuron. Let us say the first neuron. Okay, first layer, first neuron, weights are kind of, you can see here we are doing pointwise obviously, but what I'm saying is like all weights are kind of collected by I. So that way these weights get pointwise multiplied, inner product is taken, and your first inner product with the first neuron is done. Okay, then the second neuron applies, second neuron works on the same window. Okay, so then the same thing happens, just that now the weights will be different for the second neuron. So then this W first one is just the layer, so this remains the first one. W has its own set of neuron, second neuron has its own set of weights, and then this is the second neuron. So I put W2 here, and then same process happens. Do pointwise, okay, inner product, and then do activation and so on. So that way you have these values obtained finally, which are outputs from each neuron and which are scalar. Okay, so in this case, which layer, which neuron, and for which window, okay, X, Y. So that gives you those pointwise values, and then finally you save them, and then you do the activation by softmax. Okay, so X, Y, and L loop. Okay, so this is what we have, right? Overall, X, Y. This is the time loop is the top, and then layer, and then the neurons, and so on. Okay, and we can play around with some changes like we did previously. We may want to bring the time loop below. Okay, let's say. So again, these are algorithmic things. I don't think these are very difficult. So again, you can change this, and computation doesn't change. Okay, so we get the same values. So you can check that. And again, this will help us in vectorizing. If we do that change in the loop, if we bring the J loop down, then J and the ith loop. Again, the same process, because if we go and see these guys here, right? So this guy was acting on the same segment. This guy was acting on the same segment, right? So why not vectorize that, right? So let us say this is my W2. This is my W sub 1 of the first layer. So these are all first layer. So I could have done the same kind of stacking, right? W11 and then W12. And then they are acting on the same segment. Let us say in this case is this segment is X, right? So this is how the inner loop can be vectorized again in the same way like we did previously. So here this is the vectorization going on. Okay, so I can skip this. You can it's same as before. So another thing in CNN is what we have seen so far is that we start with a scanning, and as you have seen, we have a scanner, and this scanner is always fixed. Okay, like this. Okay, so this scanner is there, but this scanner is always fixed for each neurons and all the layer. So the next set of improvement that came in CNN is it is sometimes useful if you do hierarchical scanning. So scan within the scan within the scan. That's what hierarchical mean, right? It's like an Inception movie, right? Dream within the dream within the dream. And this is more or less a feature in modern day architectures, even in transformers and so on. These are multi-level architectures, and that is what is needed to extract complicated pattern. You have to build a hierarchical way of scanning. Okay, and the motivation behind hierarchical scanning is that there could be certain neurons that should focus on some smaller features. Okay, it could be eye, ear, whatever of a cat. Okay, and then there could be a neuron which is deciding on the bigger set of features. okay, then bigger set of features and so on. And finally, the final neuron should decide overall whether it's a cat or not. Okay, so that's the idea behind hierarchical scanning. So hierarchical scanning, even in the artificial neural networks, we have seen that to create a XOR, we needed a multilayer perceptron and so on. So these, and also to identify whether a point is in either of these, ideally we need a multilayer perceptron which can decide in a hierarchical way whether the point is in either of them. So why not kind of apply similar idea to CNNs, okay? And so again, what I said is the same thing is being said here, that the filter is the window size is fixed and so on. So this is the idea of hierarchical scanning, where we are saying is let us build hierarchy of filters. So as you can see, this yellow dotted box is the bigger window. Okay, let us say. So basically, you want to see different size windows. Okay, so focus on the lower windows, extract features and decide on them, then higher windows, and so on. So that's how the hierarchy, what hierarchy means here. So in this case, you have a yellow window, but for the moment, I restrict on the yellow window first, and then let the neurons scan this only within this region. So if they do, then they are kind of, so this neuron now you can see, first it will scan only within this. So let us say it scan here, then it produce one output, and then it scan some other area, then so in this case I believe it will be 3 by 3, okay? Because if you go, let us say if you go here, then you will be kind of, like stride is such that you go like this. So your strides are like that, you go like this. Okay, so if you scan like this, then this guy, if you scan this region, then you got this output, and the second neuron also scan the same region, then it got this output, and the third neuron also produce scan the same region and so on, right? And then this obviously this small white block is moving, so it will produce like 3 by 3. Okay, that's what I said, right? So overall 3 by 3 region. So finally I have shown those. So each neuron has produced 3 by 3 output after scanning only within this yellow box first. Okay, so that's what this means. And then as a next step, what might happen is that using this guys only within this yellow box, right? Now the next layer neurons are going to decide based on the output produced by the previous layer neurons only within that yellow box region, because they have scanned only this. So based on these 9 by 9 outputs of the previous layer neurons, these next level neurons are going to make decision on that. Okay, so whether some interesting feature was found with these smaller filters, and then they will produce some output. They will make a decision based on this. Not just one guy is there to produce a decision on this. The another neuron is also waiting there to provide its own verdict of what it saw in this for this yellow dotted region. Okay, so this first neuron of the second layer is saying, okay, this is what I make of this, of whatever happened in this yellow region, and then the second neuron is also going to say, okay, again I am also going to give a verdict. So and then this neuron again is processed by the third layer neuron, and it looks at the output of the previous two neuron. Okay, so it's like a multi-layer hierarchy, if you see in a company or something like that, where lower level teams work on some smaller work, and then this is being combined to see where the bigger project idea, and then finally you deliver the result hierarchically, right? So it could be seen like that. So this is what happened, and I believe the second neuron, yeah. So what happened overall is that since this neuron was only using this data, then what really happened is that this output that you get is a verdict on this yellow region. Okay, because it only saw outputs by processing done by the previous neuron only for that region. Okay, so overall what is happening is that this neuron is giving a verdict on this, and so on. Okay, so this way the process can kind of repeat and so on, and finally you will have these outputs, and then you get the final output. So only difference from previous one is that now we are doing a kind of hierarchical scanning. So this is all indeed our shared parameter network. The moment you do scanning with the same MLP, it is obviously a shared parameter network. The reason why shared parameter network is stressed more and more, it's actually because during training it is discussed. So if you are interested in that, go ahead and see the CMU lectures, because this thing, the sharing is used there. Okay, how you update the weights. But for our purpose, it's not that critical. So it is kind of evident that the 9 outputs that the previous neurons produced here, the 9 output that previous neuron produced were by the same neuron, like this neuron. So this neuron, it came up with its own filter and scanned this area, and it produced 9 outputs. So since this was the same neuron, it could be seen as if there were like 9 neurons working on that, and there were like 9 shared parameters. That's the view of shared parameter network. Similarly, there was a second neuron, and second neuron also scanned through this area, and as if there were 9 copies of the second neuron, so scanning through that area. So as if we can say that they were shared parameter networks where they were sharing with the 9 copies. Similarly with the third neuron. Okay, and then eventually this is used later on, and if we use them as it is, then obviously we are not doing a window scanning, let's say. Then moment you stop doing window scanning, then obviously there is no concept of shared parameter network there. So after that you may forget about shading. So only there you have to be a bit careful. Okay, so that's what hierarchical scan means, and this idea can be recursed, as I said, and I believe this is similarly, this is like being stressed again, so you may have a look onto these things. So this is like more or less the full flow of what is happening. All this output that we see here is just for this region. Okay, so our the way hierarchy here is like so so this yellow region, let us say, is our smallest. So this white box is like smallest region that we are scanning. So it's like we can go multiple levels. That's what I'm saying. So this is our smallest. So here the first neuron scans only the red region, then it will produce 1, 2, 3, 4. So it produced 1, 2, 3, 4. Second neuron also acts within the red box first. Okay, it's like one more level of hierarchy. First we were saying scan within the yellow region, but we are going one more level. We are saying no, let us scan within the red region first. Okay, and then produce your outputs. So these guys produced. So it's one more level of hierarchy. Okay. And then so these guys are there, right? So as if now, if these neurons are looking into these guys, then as if now you are scanning these regions. Okay, so so using this, it produced this. Okay, and then using these guys, all this. So the first level neurons gave you verdict on this guy. Okay, and then the second level neuron also gave verdict on this guy, and then this guy, and then this guy, and that is being used here by the second layer neuron. Now it is looking into all these outputs and giving a verdict on this guy. Okay, and then second level neuron is obviously it is giving verdict on this guy now, this guy now, this guy now. So it produced its 4 outputs. Okay. So now this final level neuron is giving verdict on this whole yellow box output. Okay, so this is what is happening here. There is a hierarchical scanning going on here. So this is like 3-level hierarchy. Okay, yellow region, within that I have 4x4 bigger white region, and then within each bigger white window I have another 4x4 smaller white windows. Okay, so this is the hierarchical scanning going on. So this final thing guy is deciding on this whole thing. Okay, and again, if you are done with this 3-level of hierarchy, you are happy with that, then you can final output you can vectorize and then pass it to softmax. Okay, so it depends how many level of hierarchy you want to build. It really depends on the problem at hand. Okay, so again, whatever it is again you will have a shared parameter network. So moment you are scanning only the moment you are scanning, it is shared parameter network. That's it. Okay, so so this is what is happening eventually. I can skip the shared part for the moment. So we have seen that we can do distributed scanning, and we have we obviously know we can just pick one filter and just don't change the filter size, right? So that's like non-distributed scanning. So if it is a distributed scanning, then this is what it looks like. This is a window size that you have. So this is the window size that you have. And all the neurons in the first layer has been written like this as a vertical bar. So you can think of this vertical bar as all the neurons in the first layer. Okay, so all the neurons in the first layer act on the current window. This is the non-distributed scan where the window size is fixed. And similarly, this guy goes here, and then its window size is kind of fixed. So this is looking at this guy, and then similarly they are skipping by 2, it seems. Okay, if you can see, the stride is 2. So this way, after each 2, and they miss 2, I guess, something like this. Okay, so this is fixed window, no hierarchical scanning, and reason why it's no hierarchical scanning is like, of course, it's a fixed window, and then all the neurons just act on that window. They decide on that window. Okay, so it's not really hierarchical. So, but if you see this guy, then this is hierarchical, because within a bigger window, the first level neurons are only looking into smaller size window. Okay, meaning their weights are only focused on that small. They have reduced set of weights, obviously, so they need only this many weights to work on this guy, this many weights for the work on this guy, and so on. And then this is being used hierarchically. Now whatever is being scanned in the first layer neuron is now going to produce output by this guy. So now this next layer, this guy is now making a verdict on this input, right? So indeed, overall, at least what is looking here, it's like 2-level hierarchy. Right? So we can say it's like 2-level. So first level was this much, and second level was this much. After that, it remains like that. Okay, so same thing happening for these guys as well. So there's some hierarchical scanning going on. Okay, so this is I guess the same thing repeated here, the scanning with MLP, and this is also similar to what we done before. Yeah, number of layers and all these activations is similar. There's nothing new here. Yeah, we are rearranging the computations. Okay. Yeah, so what I understand is like now we are defining what exactly is a convolution. Okay, so just to define, we have seen this already before, and so what convolution means is like this loop. Okay, so for the current window, how the current neurons are acting on that window, that's it. That's called convolution. Okay, so this we have just identified that part. Okay, so this is also we have done vectorization. Okay, so this could be interesting. So vectorization we have done. So yeah, so image goes in. Layer wise is the outermost loop, so that's the slowest. Then for the neurons in the current layer and for the current window, and window, once the segment is found, and then basically we have vectorized. Okay, so this is kind of like a dot product being happening. We can also define a tensor based dot product where W can remain like a matrix. Okay, in this case let us say matrix dot product matrix. Okay, so if we have a module, let us say in Python, I'm sure it is, so not even vector, because the neuron weights are corresponding to the window pixels, so I can just keep this in the same form. Let us say it's tensor of dimensions of 2, but if there are channels, as I said, then you will have real like 3D tensor kind of weights here. Okay, for the moment we are still into 2D, but if we make it into 3D, then if you see here, it says 3D, right? So it seems like channel has been taken into account. Okay, so this double dot, when I see, it seems like now indeed there are multiple channels in the image. So let me draw this. So actually now the image is like this. Now if you take a segment of let us say k by k patch, so this k by k patch will be taken from all RGB, right? So now indeed Y segment will be a 3D tensor, because this is now this column that you saw is through the channels. Okay, if I'm not wrong, then this guy, this is now a 3D tensor. So I could stack this small window like this. So this is like a 3D tensor. Okay, now obviously now if the filter is being applied, filter will also be 3D. Okay, so now we have 3D effect. So this guy, This guy. Actually, 3D I will discuss also later on. It seems like I will take one more half class. So there is still something remaining for the specifically for the 3D case. But it seems that here in the algorithm, already it is being written like that. So this is like the number of channels. You could say, why didn't they write 1, 2, 3? But we will see that when you go to the next convolution layer, channels may vary. Okay, so it's okay that first layer input maybe it's 3 channel, but that can be variable. Okay, so basically it says like go through all the channels for that. So then this is your 3D filter being applied to the 3D window. Okay, then in that case your W is a the filter for the current neuron is a tensor, and applied to the corresponding weights are applying to here. They are multiplying and adding. So then we can say it's a tensor inner product. Tensor inner product. So PyTorch will have that. So in a most generic sense, this is what will happen, and this is happening for one neuron. Okay, so this is for one neuron. You do this for another neuron, but of course the idea is repetitive, so there is nothing new there. So this is what this dot means, and that's how you are now dealing with tensors. Okay, so I guess I can conclude for today that. And one more thing is like just with this, I will leave this up to you to verify. I will leave this in the slides that if you do distributed scanning, then it's cheaper compared to, so this is not distributed scanning, and you can calculate the parameters used. In this case, the input is 8, and D is the number of neurons, I guess, yeah, or the dimensionality of the features. Yeah, D is dimensionality of the input here. So overall, this will be the total number of parameters, and then yeah, one can count over this, and this obviously this parameter are reused, so that's fine. So it's okay to kind of count only for one column, and then if you do distributed scanning, then you may verify this. It's easy to verify. Distributed scanning also leads to smaller number of parameters. Okay, so these are some calculations done for the distributed scanning, and yeah, and it's because it uses in distributed scanning you have opportunity to reuse some outputs from the previous layer. Okay, so we will try to continue from here in the next class. Okay, so I went in a little bit detail because when you do engineering, sometimes you play with this as well. Okay then, yeah, see you.